Okay, now we are recording. Thank you very much, gang. And then this is all yours. I look forward to hear how you are using Stan.
Right. Thanks, Bruno. Hello, everyone. Good morning, good afternoon, good evening. I'm going to talk about some applications of Bayesian modeling to neural imaging data. To start, let me use a demo data set to display, to show the problem we face. So suppose we have a fMRI data set with 124 subjects. For each subject, we have the three-dimensional data. So that data is, we have about 200,000 voxels, so volume elements. So that's the response variable Y. Then in this case, we have one explanatory variable, which is the behavior data. It's a theory of mind measure. So each subject have that value. So currently, the main approach to deal with the issue, just build a model for each voxel, right? So in this case, since we have only one predictor, we just have a simple regression for each voxel. So we end up with 200,000 separate regression models. But immediately, you would realize when we face multiple comparison issue, right? So of course, the traditional approach of bump-only correction or FDR would be just not acceptable because the penalty is too high. So fMRI has been around almost 30 years. People have tried, work on this issue for a long time, right? So gradually it has settled into two slightly different approaches. Let me use this example to show how the current way people deal with the issue. Suppose we talk about the land mass, like mountains, right? Hills or mountains. How do we define land mass is a mountain? So that's what we face. Suppose we have different land mass bodies at a different elevation, then we can calculate at that elevation the cross-section area at the base, right? So that's one approach. So if that area is above some threshold, let's say 1 kilometer, 1 square kilometer, then we consider that land mass, as surviving the threshold. So the point is to control the overall family-wise error, the nominal p-value of 0.05, right? So that's the magic number. So that's one approach. Another approach is at some particular elevation, we calculate the volume, the land mass of that body. So if that land mass is above some threshold, then we count that that would survive the threshold. So the ultimate goal, of course, is to control the overall family-wise error at 0.05. So that's the current approaches. But with that approach, we have many issues. The first one is, it's really difficult to get results to test that rigorous funnel, that filtering system, right? So on the right side, you can see there, for this particular data set, there are only a couple of regions would manage survive the rigorous thresholding. Another problem you may realize that this thresholding is pretty artificial and arbitrary, right? It's 0.05, right? So what do you call a mountain? It depends on where you put it there, you define the elevation. Of course, in the field, as a statistician, we know that this problem, if you analyze the same data, repeat that 200,000 times, we're going to face outfitting problem and also the type of M error, the exaggeration problem, the magnitude exaggeration problem. There are also quite a few other problems. So first one, under the traditional statistical framework, the frequentist thinking, since we perform the same model 200,000 times, so in the end, you are not supposed to trust the statistic at the individual voxel level. That's the reason you want to perform this so-called adjustment for multiple testing, right? So the voxel-wise results are not supposed to be interpretable. but people report that anyway. You see the tables and the brain images. They show the voxel values in T statistic. Even though those values are not directly interpretable, they're not really informative, right? But people do it anyway. So that's one problem. The second problem is a little bit twisty problem is that how do you, the clusters are only purely based on statistics. How do you associate that with the anatomical regions in the brain? So people go from the clusters to locate the peak voxel within each cluster, then use the location of peak voxel to locate the anatomical region. So they jump those several hoops. Then they say in the end, that cluster is associated with one particular anatomical brain region, right? So then you have the ambiguity about the spatial specificity because that cluster may span over multiple regions, but people can only use the peak voxel to locate one, the region with the highest statistical value, right? So there's such an ambiguity issue there. Of course, if we want to interpret it without the cluster level, then people have trouble assigning the uncertainty, right? So you can't get, I mean, for example, uncertainty interval or whatever standard error for each cluster. Of course, people in the field know that there's a discrimination problem. The small brain regions are really difficult to get to survive the thresholding, right? But people have some tricks. For example, one trick is to manipulate the data, the so-called small volume. Even though data is the same, but people say, I only want to focus on this particular network or region, like a frontal cortex, for example. Suddenly you change your view, then the statistical evidence will change, right? The p-value will change. Is that a little bit tricky or I mean, too manipulative? But people do it anyway, right? So those are the problems. But I think the fundamental issue is that people adopt this, make a strong assumption about the distribution in the brain. So do we know anything about the distribution in the brain? Well, people say we don't. We don't know which region response is bigger or smaller. Yes, we don't know that. But we do know the distribution. I'm not saying the distribution like the specific like mean or the variance. It's not about those two parameters. It's about the distribution, the shape of the distribution. I think we do have some of the information. We can reasonably assume it's at least approximately it's a bell-shaped. We can use Gaussian distribution to approximate that distribution or even T distribution. So is there a way we can use that spatial information? Well, the traditional approach assume we know nothing. So that's why I adopted a uniform distribution. For Bayesians, that's just, I mean, you adopt the attitude of, we have no information, right? So I think we could more efficiently to leverage that spatial information. So since we can reasonably assume the distribution as, for example, Gaussian to start with that prior, then we can do something about it. So for example, let's go back to the original data I mentioned with 124 subjects, right? So let's, as a proof of concept, focus on 21 regions. So same predictor, that's the behavior data. Instead of building 21 separate models, we just build one model by incorporating those 21 regions into that model. So with that one model, we have two separate groups of effects. One is the overall effect. That's the parameter A and B, right? So we have the intercept plus the slope. That's the overall across all the subjects in the regions. Then we have this cross subject variability. That's a pi sub I. Lastly, we have this region level effects. So we have those 5 parameters. Then we have the priors. Let's just say they follow Gaussian distribution. With that, I already implement the approach into a program in the Affinity program that's for rearranging data analysis using BRMS. So let's see what can we get. So in the end, we care about the each region level. It's not about the overall intercept or slope. Instead, I mean, most of the time, I mean, we're interested in at each brain region, the intercept or slope, right? So that's we want to focus on. So we put the data into this data frame, right, long format. Then we run this script. So just specify the input, what we want in the output. Once we do that, then we get the posterior distributions for those 21 regions. So we present the 4 results. So unlike the traditional approach, you just show, I mean, this is typical in neuroimaging, right? So you just show the brain, you just show whatever you consider it's based on rigorous thresholding, only 2 regions in the brain that can survive. You consider that, you call that randomized bodies as mountains. Anything, the rest is just nothing in the brain happens, right? That's not true. I mean, we know most of the brain regions are engaged most of the time, even during rest. So that's a pretty, I mean, distorted interpretation of the results. So with the Bayesian approach, we propose, we present the 4 results without hiding anything. You can highlight, discuss some of the regions that with strong statistical evidence, but they don't have to hide the rest. I mean, more importantly, unlike the traditional approach, you could only report those 2 regions. So in here, we with the Bayesian multi-level modeling, we probably will have almost 10 regions you can consider you have strong statistical evidence. So in addition to the showing the results, we can also validate the model, how good the model or how bad the model is, right? So as Bayesian, we know you can do a leave one out cross validation using the information criteria to compare 2 models. So using that information criteria, immediately we realize that the Bayesian multi-level modeling approach is way much better than the traditional so-called massive univariate approach, general linear model. We can also do a posterior predictive check, right? So to use the models to randomly generate the simulated data. So on the left hand, I mean, the blue one, the blue cloud is the Bayesian multi-level modeling approach, the simulated data. The black curve is the original data. The right-hand side, that's the traditional approach, massive univariate analysis using a general linear model. So that's the red cloud. So with this comparison, visual comparison, we see also the Bayesian multi-level modeling approach is way much superior to the traditional approach. We can also apply the same idea to a couple of other scenarios in neuroimaging. Here, I'm going to show another example is suppose each subject have a correlation matrix. In fMRI, people calculate the correlations among a list of number of regions. So each subject will have a correlation matrix. How to summarize that those are correlation matrices cross subjects? Well, as a traditional approach, each element in the matrix, people just perform t-test, right? So then in the end, you still face the same so-called multiple comparison issue, right? So we can adopt the same idea. Instead of build a separate model for each matrix element, we build one model by incorporating all the regions and the region pairs, in this case, matrix elements into one model. And make assumption through Gaussian or T distributions. Then we sample the results. So same thing, but it's just the same concept. So we can do that, and there's a program available too using BRMS. So that's one application. Another extra application is that the notion of test-with-test reliability, right? So people have been using this for decades, right, to measure the traditional concept of intra-class correlation, right, for individual differences, right? So people have to do this for, many years. The traditional approach, suppose you have experiment, you repeat the same experiment 2 times. For each condition, you have the number of trials, right? So the traditional statistic, you will aggregate the data, right, across the trials. Then for each subject, end up with the contrast between 2 conditions. Then you build an ANOVA model, then calculate the correlation. In this case, it's called the intra-class correlation, right? That intra-class correlation can be interpreted either as correlation or as the variance ratio, right? So that's the traditional idea. But that we do have a problem here, because usually the experimental design is not at the condition level. For each condition, you have many trials. So the traditional approach, basically you aggregate the data across those trials. So that's called a summary statistics. That's immediately we lose some information. So instead of aggregating data, we put the original data into the model at the trial level. So if we do that, we build a typical hierarchical model framework with the priors, with the variance covariance matrix. We can calculate the correlation between those two sessions. So if we do that, and if we go through some theoretical deviation, you would realize the traditional concept of ICC can be substantially underestimated. That the amount of underestimation can be characterized as the proportionality. That proportionality is always less than 1. So this points to the serious problem of the traditional concept of intra-cross correlation when it is applied to an experiment design with multiple trials. So that's a problem. So this hierarchical modeling problem not just improves the accuracy of the estimation, and also points to the problem of the traditional concept. And with the hierarchical model approach, we're not just getting a point estimate, we also obtain the uncertainty information, either in the form of a posterior distribution, or you can get some quantile intervals. So this is also implemented using BRMS instead. So to recap, I start to address the fundamental question: whatever the effect we talk about in the brain, do we know something about their distribution? I think the answer is yes. It's not reasonable to assume Gaussian distribution. I mean, it's not reasonable to assume uniform distribution to waste the information. Instead, we could adopt an approach that can leverage the information across the brain. So with that, the rest is, as a Bayesian, we can just, to go through the typical model building and the model validation steps. Last, I just want to thank my collaborators and also Paul and the Stan development team for their strong support. All right, that's all I have. Thank you.
Okay, thank you very much. So if there are questions, you can write them in the chat and I can read them. In the meanwhile, I have a question. So how many observations do you have in like a typical model? You have the voxels times subjects times trials. So how many are they?
Subjects, that varies. Usually, the typical, it's probably from nowadays about 20. The upper bound can be thousands. Now there's a big data initiative. So, but the typical, the individual study, usually it's about from 20, I would say from 20 to 100. That's the number of subjects. Number of voxels is probably in the order of 100,000. Can be more, can be less, depends on the resolution. Number of conditions, that also depends on the experiment, can be just one or a few, or can be several, conditions. Number of trials, that's another important issue, actually. Typical design, people usually put it, for example, 20 trials on average, 20, 30. That's the typical way. That's just the, so the subjects, the participants could tolerate in the scanner. That's usually the case. But from experimental design perspective, of course, the more the better. That's just like the sample size for subjects. The more the better from statistical efficiency perspective. But there are practical considerations. People usually, currently, the typical is from 20 to, for example, 50 trials.
Okay, yes, but my point is the amount of observations that you have is insane. So how long does it take to run these models?
Yeah. For the data, I didn't do the whole brain at the voxel level. I only did for that there are 21 brain regions. In that case, it takes about 10 minutes.
So you
but if we do whole brain at the voxel level, like for example, 200,000 voxels, that's just not practical at the moment.
Okay. Yeah. Yes. Yeah.
But my counter argument is that you don't have to focus on the voxel level. That is not what the typical research is, aiming for. In the end, the research hypothesis is always about the brain regions. So I think for most studies, you could just focus on a list of regions. From 10 to up to 1,000 regions. There are different ways to define those regions. Of course, there are some extent of variabilities about the region definitions, but that's a different story.
Okay, there are more questions, but before I move to the other question, so in those regions, you average across voxels or you sum the voxels, right?
Mm-hmm.
Okay, so that's how you get rid of the individual voxels. You average them.
Oh, no. Oh, yeah. Within each region, you average. Yes, you average. Well, you can do average or you can do a principal component. There are different ways. Yeah.
Okay. Okay, so John C. from Noi has a question. Can you say a little bit more about your approach to leveraging spatial information? Does it increase compute time very much? It's such a great idea.
Well, a little bit more about leveraging spatial information. In this case, in the demo data, I had 21 regions. So the leveraging basically here, I assume Gaussian distribution or student T. I usually probably prefer student T distribution because it's more flexible, more adaptive to whenever you have outliers or the distribution may be skewed. So student T, I usually recommend. Of course, you can do try different models, then compare them using, for example, information criteria and posterior predictive checks to verify which model is more reasonable than other candidates, competitors. So that's what I mean by leveraging spatial information. Basically, it's, from statistic term, it's called shrinkage or partial pooling, right? Information sharing. Instead of like the traditional approach in fMRI is you adopt the agnostic, right? You assume that you don't know anything about the distribution in the brain. That's why you you build a separate model for each voxel or each brain region. So you waste a lot of information. You can argue that the typical multiple comparison step, they take into consideration of the spatial information, but that spatial information is only limited to the local information among the neighboring voxels, not globally. So the global information, the Gaussian distribution, for example, is still wasted. That's why we pay a lot of penalty on that on the adjustment for multiple testing issue. I'm not so sure, John, does this address the question about leveraging spatial information?
Yeah, thanks. And I think the next question is relevant too.
Yeah, so Henrik Zingman also asked something very similar or related.
It was the same question.
Yeah, yes.
Oh, okay.
So I'll retract my question, thanks.
You could argue because different brain regions, different brain networks, they may have another hierarchy, right? So for example, visual cortex, they have their own clustering, right? So you could incorporate another layer of hierarchy because that hierarchy is across different brain networks. In theory, you could do that, but that needs more further investigation. So that is something we need to consider that in the future.
Okay, and Fabian Munoz also asked something related to what I asked in terms of PC power. Which kind of setup do you use and how long is it taking to run a model? Yeah,
that for fMRI, that's the only part I have experience with. So for power, it's since now we have in Stan, we have this within chain parallelization. So the more CPUs, the better. It's now you can. In probably like a couple of years ago, or even 1 year ago, I could only run with using, for example, 4 chains. That's the only thing I could use, even though I had more CPUs, but you could only use 4 for those 4 separate chains. But now since within chain parallelization is available, now this substantially improve the computation time by 2 to 4 times. That's my personal experience.
Okay, there is time for another question if someone wants to ask something else. And a small question in the meanwhile. So you mentioned some other packages like AFNI. So these are packages that rely on VRMS. There are packages that run the type of the statistics that you need. Can you say something about them?
Sorry. In FMI, in neural imaging, there are separate packages. Like there are 3 major ones. I think there's a SPM, and there's a FSL. AFNI is one of them. So it's the AFNI is basically specifically for FMI data analysis. So the few programs I mentioned in my talk, like the region-based analysis, RBI, MBI, that's for matrix-based analysis. Then there's test reliability. Those 3 programs are written in, using R and BRMS, but it's part of the AFNI package for neural imaging data analysis specifically.
Okay, I see. Henrik is asking, what criterion do you use to determine if a cluster is significant?
Oh, that's for the traditional approach, like the so-called massive univariate approach, right? So the cluster, basically, I was trying to use the mountain as an example how people define a cluster. So there are 2 ways, as I mentioned. One way is you set a threshold. For example, the voxel-wise p-value of 0.001, for example, you consider that as your elevation. So now you compute that cross-section area in that mountain. So anything, if that cross-section area is above 1 kilometer square, then you say, okay, those body land mass I can consider as mountains. That's the traditional approach. So for Bayesian multi-level modeling approach, right now, I haven't done at the voxel level. That's because of the computational problem. And that's just currently prohibitive. It's not possible. So we directly focus on the region level. In that case, we don't need the notion of clustering because you directly find the regions in the brain, right? So what you get is you can directly interpret the results at the region level. You don't need to worry about the voxels or clusters. So that's another benefit of directly focusing on the region level instead of voxel level to avoid that the interpretation problem.
Okay, and then Johannes has Alger Missen has a question also related to spatial relations. So he's asking, if you discretize a brain into regions, how do you encode the spatial relations between them? Just distance between the geometric centers? Isn't that quite strongly influenced by your definition of those regions? And wouldn't your solution then also scale to EG or MEG?
Well, I probably briefly hinted a little bit about well, there's sometimes some regions may not be available, currently available, as a defined, because, for example, visual cortex is so complex, right? So there's so many sub-regions. You may not be able to define all of those sub-regions. So that's one difficulty. It's not about it. You don't use the distance among regions to specify their relationship. Well, right now, most of the time, I think Gaussian distribution or student T, it's good enough to leverage the information among them. I think that's you could argue some regions are more related to than others, right? So my answer to that, if you have extra information, you can group them. So then you build another hierarchy. So into the model that we have done that in a separate study. Yes, that is one solution. Another thing I can argue is that, we don't need to assume those regions be independent with each other. That is not required for Bayesian hierarchical modeling. The only thing we need is the exchangeability. It's not the independence. So that's for hierarchical modeling. It's the exchangeability that is required. That's the only assumption we need. So for most of the cases, I think that exchangeability is met most of the time. So that's usually I would not worry too much about that. For EEG, MEG, I don't have any experience. I think it can be applied, but I don't have personal experience so far. But I would love to try it out if there's such a data available.
Okay, thank you very much, gang. That was super interesting. Now the next speaker is Henrik Zingman, that is going to replace Kendall Foster, so it's a joint work. Whenever you're ready, you can share your slides, Henrik, and you can start.
Can you hear me now? Yes?
Yes.
Okay. Okay, great. Sorry. Okay, yes, here we are. Yeah, thanks so much, Bruno, for organizing this, and thanks so much, everybody, for voting for this talk first and then attending here. Yeah, this is joint work with Kendall, who unfortunately plays quite a bit of soccer and recently got into a soccer induced alteration with somebody and is suffering from a concussion. So I'll have to take over today. I'll be talking about an implementation of the diffusion decision model with a cross-trial variability in the drift rate. And we have already started. I mean, whenever I say we, I mean Kendall, unless it's an error, then it's my fault, of course. So Kendall has already prepared a lot of this stuff, and it is available on GitHub. Check out GitHub/kendallfoster/DDM_in_Stan, and there's already the first draft of the document. Okay, so what are we going to talk about is a simple experiment. I want to start with an introduction and like a motivating example. So imagine you do a simple lexical decision experiment. So participants see letter strings, and their task is to decide, it's a binary choice task, is it a word or is it not a word? Here, house, they would say it is a word, or it could be some non-words and so forth. So you do this classic experiment where participants do this task. The outcome in such an experiment is usually multivariate. You have two different responses, namely you have participants' choice and you have the response time. And the problem is that these are not independent. So for example, here is data from an experiment that has manipulated accuracy and speed across two conditions, simply by instruction, telling participant in the one condition, hey, be as accurate as you want, and in the other condition, hey, be as fast as you want. And what we see here is across participants distribution of mean error rates and mean response time. And we see that participants can trade them off. So in the accuracy condition, they are relatively correct, but slow. And in the speed condition, they're a lot worse. So accuracy is lower, but they are faster. And this is a general problem that we kind of have to address. How can we model, how can we describe data where these two components jointly contribute to the observed behavior? And of course, the most popular model to address this kind of data is the diffusion decision model. The idea of the diffusion decision model is that these two, the conditional response time distribution, arise from an evidence accumulation process. So the idea is that on encountering the stimulus, the decision maker accumulates evidence for one of the two responses. And in this case, the responses are word or non-word. And this is a noisy accumulation process that as soon as it hits one of the boundaries, the word or the non-word boundary, the evidence accumulation terminates and the corresponding response is given. And this model allows to separate the observed behavior in the basic variant into 4 parameters. We have the drift rate, the quality of the rate of evidence accumulation, boundary separation, or response caution. And one of the ideas, for example, that if you change the instruction from accuracy to speed, this would have an effect on the boundary separation, where you accumulate more evidence when you are in a situation in which you want to be very cautious, leading to longer response time and lower error rate. you also have start point, which is the bias or relative bias towards one of the two response options. And you also have non-decision time component, which is everything outside of this kind of graph showing the DDM, motor process, perceptual processes, and so forth. This is the relatively standard DDM. And the good thing is this is already implemented in BRMS. So if you want to use this, you can go ahead and use BRMS. Just put up a library BRMS, and then you can essentially create a formula for each of the 4 parameters that I just presented. So you just have to specify both the response time and the response, binary response, 0, 1. And then you can put a formula on the drift rate, boundary separation, non-decision time, and the bias. And then you can just fit it with BRM, and that works. And you can use all the BRMS functionality, posterior predictives, and so forth. Can look at the parameters. If you want to know how to do this, I have written a series of blog posts that you can check out. However, there is another variant of the diffusion model, the 5-parameter diffusion decision model, which assumes that across trials, the drift rate is itself coming from a distribution, namely a normal distribution. So the idea is that across trials, drift rate is normally distributed. And if we add this parameter, we can, so the addition of these parameters allows that the relative speed of these two distributions, the response time distribution of words and non-word responses, for example, if we stay with our example, can shift. The mean response time can shift even if we are in an unbiased situation. The normal 4-parameter model cannot do this. So in the normal 4-parameter model always predicts that the means of both distributions are the same unless you switch the bias, which is, of course, often it happens that this is not the case, that the means are not the same. Drift rate variability is one way to allow that these are different even without a bias. So it is kind of an interesting idea. Could we add this also to Stan? The problem, of course, is that the DDM density function is not very simple. Let's use this word. There are 2 different variants of the DDM density function, namely, so there are 2 mathematically equivalent formulations of how the drift diffusion model can be specified. And the one is called the large time variant, and the other is called the small time variant. And the idea is that both of them have differently favorable numerical properties depending on whether the response time is large or whether the response time is small, hence the name. However, as you can see here in the blue parts of the formulas, both of these have infinite sum in them. One of the infinite sum includes a sinus term, and the other here the exponential term only, but both of these include an infinite sum. So if we want to estimate, calculate them with a computer, we kind of have to figure out where do we truncate these infinite sum terms. And there is quite a little bit of literature out there and how to do this. And of course, if you implement the DDM function, you also have to implement a switching algorithm between, when do you pick the one, when do the other, and how do you truncate the infinite sums. Luckily, we already, again, we saying Kendall mostly, have looked into the literature and figured out how to do this and how to implement this, and have also kind of come up with a new way of truncating and combining these two. And we implemented all of this already in an R package, which is called FDDM. So if you just want to see the implemented this in C++, so if you just want to see a C++ implementation of the 5-parameter variant, have a look at our archive paper and our package. But of course, the question of this talk is something else. Can we get this 5-parameter variant also into Stan? That was the start point that we want to go. And this is the answer to this is a long story, and I want to give a little bit insight. How does this happen? So, okay, what is the first approach that you're going to do can we get the 5-parameter DDM variable to Stan? So you can, take a look at the Stan documentation. How can we add new distributions to Stan? If you do this, you'll see the idea. You add it to Stan Math, and then you put a pull request. So of course we did this. Now we implemented everything. So we added. I don't know if you can see this, but we added the CDFs and the PDFs and the corresponding tasks, and tried it out, and kind of it seemed to work initially for us. And then we opened the pull request, but this is still the status of the pull request is still that from 20th of September. We ran into a few problems. So this is the recommended approach, but we ran into a few problems. First of all, programming it for the Stan Math library, which includes template metaprogramming, is non-trivial, even though we already had the existing C++ code for our package. So everything there is no R, it's just C++. Converting this to the Stan Math functionality, which uses this template metaprogramming, that is a not trivial matter if you're not, if programming is not your main occupation, because this is a little bit additional work required. Yeah, not easy to do. Implementing the tests is also not really clear. It's not very well documented. I mean, I don't want to put any shade on the Stan Math developers. This is it's difficult to figure it out from just looking at the existing code. And another problem that we figured out, so you can implement it in Stan, and then you can compile the Stan Math library and see at the command line that your implemented function work. However, we were not able to find a way to use this in our own Stan model. So then compile RStan or CMD Stan R to actually use this in a model in a productive manner. We couldn't figure it out. And Stan developers were also non-responsive to our pull requests. So in the end, this didn't work out for us. So if you try this, this is not an easy way to go. We spent some time on it, but we couldn't get anywhere. Again, I don't think it's a problem with Stan developers, probably our inability to do this, but just as a cautionary tale, it's not trivial to get this in there. So we tried something else. I'll get back to this a little bit later, but let's just say our second attempt was to implement it as a custom family in BRMS. And it turned out, this worked reasonably well. So you just define a custom family for now the 5-parameter that you have, and we all, because the parameter have different bounds, you have to specify link functions. Then you just have to write the whole likelihood function in the Stan code. That I'm hiding this here, of course, it's because it's quite long. You can see this in our Markdown document. Add this to the function block, specify a priors, and then you're essentially ready to go. So the first thing we tried out then is let's simulate data from the diffusion model. Our diffusion in this package is a good function to simulate from it. We did this, and then you just have to add, because it is a multivariate likelihood function. You have the RT and the response. You still need to add the response from the data to a variable to your Stan program, but then you can simply use BRM to fit the model. You see very simple BRM code. We have there's no variability. We only estimate the 5 parameters, only the 5 intercepts. Very thing. And let's have a look at the results here. Here, these are the generating values again, -2 for the drift rate. And we can see here the recovered drift rate is around -2. That seems to work for, remember, we generated 1,000 observations. The boundary separation A was generated at 1. We covered as 1. Nicely, we covered the non-decision time, generated 0.3. We covered as 0.3, also works very well. The start point here generated as a 0.5, so unbiased, recovered nicely. And the SV is the drift rate variability. We generated 0.8, recovered as 0.5, so not perfect, but it is kind of well known. So there's papers out there showing that recovering this parameter is kind of difficult. At least we're, you know, somewhere in the ballpark. If we look at the Bayesian credibility intervals, we see it includes the true generating parameter. The question then is kind of what do you gain from using the 5-parameter model? You know, that's kind of one of the questions we could ask. So we also fit the 4-parameter model to this generated data. And what you see here is if we do this, here again are the generating parameter values. This is simply the 4-parameter model. Boundary separation is no unbiased. Non-decision time and bias are also unbiased, but we see a bias in the drift rate. So if you fit the 4-parameter model to a model that has also drift rate variability, you see that the actual drift rate parameter is slightly biased. And you can have a look again here at recovery of the drift rate parameter. So the true drift rate was 0.2. And here we see the posterior distribution in the green is for the 5-parameter model that kind of is around this true value. But we see here we have 2 different variants of the 4-parameter model, the one implemented in Stan and another one, you know, that's just based on like another custom family based on our code. They are kind of slightly biased. But we see the distribution is a little bit tighter. Yeah, so that seems to work. One more thing I want to say here is fitting times. The 4-parameter variant, it doesn't matter which variant you use, where for this data set, roughly 40 seconds. However, for the 5-parameter variant, more than double the length of that. So adding the additional parameter increases fitting times quite a bit, and by more than 100%, we would say so far. Okay, so next point is how do the priors look like? As a reminder, we set up the custom family such that we used like a generalized model. So we used this link functions to get in the allowed range. Only the drift rate is supposed to be unconstrained. The other parameters are all either go from 0 to infinity or from 0 to 1. So we use the log or the logit transformation. And we needed to specify, however, our parameters, our priors, of course, on the unconstrained range. So we needed to see how do we get good implied priors. And we could see here, this is the priors that we came up with for the mean parameters. And you see they're reasonable. So for A, kind of it peaks between 1 and 2, which are common values. For the non-decision time, you want that it's like in this region. For SV, you want it not much larger than 1, so it worked. And here for the W, it's peaked around 0.5. So we kind of came up with good priors. We think that feel free to use. Because we have implemented this as a custom family in BRMS, we can, of course, also use BRMS functionality. For example, we also have the log likelihood function, so we can use LU. And what you see here is if you compare the LU for the 5-parameter versus the 4-parameter variant, you see that there is essentially the information criteria do not provide evidence. Even in this, you know, we only estimate either 5 or 4 parameters, and we have 1,000 data points generated from the 5-parameter model. In this case, there is no evidence for the 5-parameter model. I mean, there is very, very slight evidence, but not the evidence does not exceed the standard error of the ELPD difference. We can also, or we did also wrote a posterior predict function, of course. So you can also simply run pp check on the fitted model object, and you get posterior predicted distribution values. They look fine here in this case. Okay, let's quickly sum this up. Can we get the 5-parameter DD variant into Stan? So adding the response distribution to Stan math, the official kind of way is difficult and we failed. Our main issue, I mean, we couldn't get it accepted, but the main issue is essentially that we couldn't test the function in a Stan model. So you can add the function, you can make a clone of Stan math and add something there, and then you can also compile it, but we didn't figure out a way to then actually use it either in RStan or CMD Stan R. If that would be maybe better supported or a better way, I think that would help in getting this done. And there is also a description actually on RStan that said you can add external C++ code. We also couldn't get this to work, mainly because as soon as we tried to add it as a likelihood function, that didn't work. Not sure, like it also is not something that we couldn't figure out in reasonable time. However, it was possible to add it as a likelihood function directly in Stan code, and then by using a custom family, we got full BRMS support. If we compare the 5 parameter to the 4 parameter variant, 5 parameter variant recovers the generating parameters quite well if you have enough data points. Applying the 4 parameter variant to the generated data from the 5 parameter model leads to biased drift rates in the presence of drift rate variability. However, even with 1000 trials, Lua does not support the 5 parameter variant. Oh, it's kind of difficult to get support there. The time is up. I did have 2 or 3 more slides on fitting real data. How should we do this, Bruno? Should we stop here?
No, you can continue. We have some extra time because of.
Okay. Cool. Okay, so can we fit real data with this? This is what we tried. So because this factorial data, we first set the contrast in the R session to this orthonormal contrast. Oh yes, that you need. I think you need to use you need to load the base test R package first. It's also in the R Markdown. You'll see. Here we use this data Redcliffe. Then you can also specify a formula for each of the 5 parameters. The RT in this case is the drift rate, a boundary separation, non-decision time, and start point, and also SV. Here so far we only fitted the fixed effects model, no random effects model. I'll get back to this later. We wanted to disable the automatic centering of BRMS. We didn't want that our model matrices, because we already use orthonormal contrast. We didn't want additional centering here. This is, be aware, if you want to do this, you have to set both center false, and you have to use the 0 plus intercept for all but the first formula. Otherwise, centering of the model matrix will not be implemented. That seems to be something specific about custom model formulas in BRMS. Then, in this case, you also need to kind of adopt the priors a little bit, because you want to have different priors for the first parameter, which is the intercept, and then, of course, all the other regression parameters, which are differences from the intercept. We did this, kind of left the first parameter to this, and to the others simply T parameters with this given scale that we felt was reasonable. And then, almost ready to fit, only one more wrinkle together. Actually, to get the model to fit, we needed to create a specific function that produces start values. Without this function, that didn't work. So we need to have a start value function in there. And yeah, this will also be in the document, because the problem is, if the start value for the non-decision time is larger than the smallest non-decision time, then the model produces a likelihood of 0, and then you cannot get started. So you need to ensure this is the most important thing. And so you need to have a function that ensures this. And yeah, we kind of figured that out. And then you can just, again, use BRMS to fit the model. So far, we fit both the hierarchical and non-hierarchical model. After like 4 or 5 days, only the non-hierarchical variant converged. We see the results here. This is simply the BRM output. So what you get out here, because we just fitted this very simple data that we showed in the beginning, the data from Wagenmark et al. With the lexical decision task. So we have only two conditions. The conditions is speed versus accuracy, and then we just have two different item types, which is frequencies here of word versus non-word. And here, what I've highlighted for you is where do we see all the condition-specific parameters? So where do we see differences? For the drift weight, we only see differences in whether it's a word or non-word, as we would expect. And then we also see an interaction between word and non-word and condition. And so speed, accuracy, trade-off manipulation. Such things have been reported before. As expected, we see that the A parameter differs across conditions. So boundary separation, of course, is affected by whether or not you use speed, accuracy, trade-off condition. However, we see also differences in the non-decision time parameter and not in the bias, which is fine. All these things have been reported before in the literature. Because we have here data from multiple participants, not sure how much money one should put in this. Nevertheless, the SV here is estimated, if you transform the spec onto the actual parameter scale, is estimated to be around 0.3. Okay, so let's sum this up. Adding new likelihood functions to Stan math is a not trivial endeavor. Now, if you try to go on this path, be ready to invest some time. However, even complicated likelihood functions can be added directly as a Stan function. And then you immediately, if you use a custom family functionality, you immediately get BRMS functionality, which of course simplifies specifying the model tremendously. I highly recommend to do this. The 5-parameter DDM can cover parameters as long as you have large enough number of parameters. However, it's difficult to find evidence for the 5-parameter versus the 4-parameter variant, and the 5-parameter variance is also considerably slower, at least double the speed. Fitting the data to real life in BRMS requires some additional tricks. If you want to disable centering, you have to use the 0+ intercept syntax. The start value function is definitely necessary because the non-decision time cannot be larger than the smallest RT. Otherwise, BRMS will not start sampling. And after like 4 days or so, the hierarchical variant has not yet converged on our servers. So we will keep you updated whenever this is done. And yeah, that is it from me.
Okay, thank you very much. That was super interesting. So again, you are welcome to post your questions in the chat. And in the meanwhile, I have already a question. So one of the reasons to code directly in Stan is to, directly in C++, is to specify manually the gradients, right? Because if you don't do that, and if you use, if you code directly a likelihood in Stan, then Stan does auto-differentiation, which might be slower if you have nice gradients that you can derive analytically. So was it the case here for this likelihood function?
No, we don't. I mean, there is the gradient. I mean, we use automatic differentiation, but like our first implementation, even the C++ implementation, did not use the gradient because, like, programming this meta template programming is really, this is really, it is not simple computer science stuff. So I mean, it doesn't matter. In the end, we don't have any.
No, my question is if it's, I mean, given that so much travel, I never did that, but if it's worth it, because the only reason to do that would be to also to manually specify the likelihood in this template and also the gradients. But if you are relying completely in auto-differentiation, why would you go through the trouble of implementing the function in C++?
I mean, why would we go to the, I mean, because that, like, I mean, we tried it out. I mean, this.
Yes. Okay.
First of all, you have to start somewhere. I mean, one of the ideas surely would be to kind of get the automatic. There was a recent paper from the Freiburg group that showed the partial derivatives, so they are out there. So it could be done, but yeah, we first have to. Yes. So the partial derivatives are in the literature. There is also an R package. They're only available right now in pure R code, which of course makes them kind of slow. But yes, so the partial derivatives are there. It could be done, but I don't think you would have to have you have to be a good programmer. You have to have heard.
Then it makes sense.
Heard of meta template programming. If you haven't heard about this, then forget about it.
Yeah, that's a pity. Then yeah, so maybe the difference in speed between the two models is because one is implemented directly.
No, it is not. The 4-parameter variant does not have the as far as I know, doesn't have the partial derivatives. I'm pretty sure it doesn't.
Okay.
I looked at the code. So there was only a recent paper which showed them. Just very recently, they're only recently out in the literature.
Okay. There are already questions. Yeah, it's really a pity that one cannot simply include new functions. Yeah, I don't know C++, so it's completely out of my possibilities to implement a function like that.
Yeah, I mean, we use some C++, but yeah, as I said, kind of there is just an additional layers, and then there is the issue. I mean, I'm not I think Stan is one of the greatest things. So whatever I say, don't misunderstand me that I want to say anything bad about Stan. Surely not. This is just that kind of. So Stan math is something else than Stan. So there's just additional layers, and it just gets very complicated if you're not a programmer, which neither of us is.
Yeah, I'm not representing Stan, so it's not that you are.
Yeah, no, I don't mean it, but I know there's Stan, there's Stan people lurking around.
Okay, so Anna Martinovici is asking, on a hierarchical model not converging even after 4 days, this was with the real data, I think. How does it work with simulated data? Is it equally slow?
I mean, we haven't tried. I mean, we just tried this wanted to try this real data out. This was the first thing we tried. We didn't try any simulated data or hierarchical data. And yeah, so we cannot tell you. But I know if you fit this, so the data that we're using there is the same data I used in my blog post. And there, I think it fits usually within 12 hours, just the 4-parameter variant or so. So yeah, it's, but it hasn't yet converged. And I don't think it has meanwhile.
And also she says, I heard from more people that hierarchical models are very slow in VRMS for DDM. I'm just curious if you have an intuition for what can impact the speed.
I mean, I think it's, I have the same experience. I have models that are I have models that literally ran for 3 months, hierarchical DDM models. No joke. Especially then also generating the posterior predictives can also be insanely slow, can also take days. If you have like I had a few 100,000 data points, and then it just takes quite a bit of time. I have no intuition. I just know that it takes time, and I'm very, very certain that if one were to implement, I'm not implement the gradients, which are now available since this recent paper from Raphael Hartmann and Christoph Klauer in a Journal of Math, came out this year or last year. If one of the people who knows Stan can implement them, add them at least to the 4-parameter variant, I think this would be great. It would be absolutely awesome. But yeah, I think this needs somebody who really knows the ins and outs of the Stan code. I'm happy to post the picture. I tried. I see Jan Gottman. I've tried within chain parallelization. I've only used 2, and that seemed to slow down. In my experience, that seemed to slow down fitting. Using CMD standard within chain parallelization. I haven't done rigorous testing, but my impression from trying it out is that it is slower than just at least 2 chain, than just using a single chain.
Okay, and then and so on. What about OpenCL with a good GPU? Have you tried that?
I haven't tried it.
And by the way, is there evidence from somewhere that we even need this parameter? I mean,
I hope
possible to know.
I mean, but it is clear. So if you only fit, if you only fit a correct and error responses, then the bias has to be fixed at 0.5. So if your coding is correct error responses and you don't fit responses correctly, your boundaries are not the actual responses but correct and error, then the bias has to be 0.5. Then the model has to predict that the average speed between correct and error responses is the same. No, there is no other way. I mean, if you live with this, so theoretically, we definitely need it, but there is also clearly research out there. I mean, there was a recent paper by, I'm also on the paper with 20 other authors. So I forgot whom. So where a lot of groups try to recover these parameters, fitting these parameters like just numerically is extremely difficult. So in theory, we need them, but actually using them in practice is insanely difficult. You need thousands of trials to estimate them. If it makes sense, if there is any practical reason for using them, kind of unclear. I would probably say it's not worth the hassle.
Okay, but here you're mentioning when you're assuming that the bias is constant because you are using accuracy coding, but if you use stimulus coding, you can always attribute the difference to the bias, right?
Yes, but is this, yeah, this is the only way. If you use stimulus coding, you can use bias, but yeah.
Okay. And Jan Gottman is asking, is the drift variability being related to an external measure like intelligence? Are there empirical results?
I mean, given how difficult they are to estimate, I think estimating them on the individual level is kind of not a good idea. I don't know any, I'm not aware of anybody doing this, but I don't think we don't have enough data.
Okay.
There's Blair.
Sorry?
Blair
yes, hi. I just wanted to talk on this point about estimating cross-trial variability parameters on an individual level. So Roger Ratcliffe has some work showing that it is actually pretty important to do so when accounting for data in certain tasks, specifically those where the overall magnitude of the stimuli is varying. So he shows that as overall magnitude increases, there's more variability in the decision-making process, which you need this cross-trial variability and drift rate parameter to account for.
That's the thing. So clearly, theoretically, I mean, it's difficult to say. Of course, Roger Ratcliffe would say this because this is kind of the big idea of his 1978 paper, which kind of, like led him to have this incredible career. So of course he must say this, but yeah, I mean, I guess it's one of these things where the variance bias variance trade-off. Like, should we do it? Yes. Can we do it? It doesn't look like it. So unless you really have thousands of trials, it seems a little bit problematic to include it. Yeah, just from an estimation standpoint. But yeah, this is just my opinion. Roger Ratcliffe definitely has different opinions.
Okay, then yeah, thank you very much. That was super interesting for me, at least, and I guess for many people. There were a lot of responses. And now the last speaker will be Jan Gottman. So whenever you're ready, you can share your slides. Mike Lawrence won't appear today. He said that he will upload his presentation at some later point.
So hello, do you see my slides?
Yes, but also your notes. Okay, yeah, now everything.
Yeah, and you hear me? Okay, that's nice. So thank you for having me, and thank you, Bruno, for organizing this the session. And yeah, I will give a quick introduction to my research project, which I realized with Stan, and I hope you will enjoy this. So the main question I'm asking is like, which processes are captured by, for example, a complex span task? And there could be many answers to this question, like working memory capacity, attentional control, processing speed, short-term memory, or in general, many people would say it's like cognitive ability. The problem is here that we measure this all with two measures, like reaction times and accuracies, and we don't really know how confounded these measures are, or how confounded these processes are in these two measures. So complex working memory processes are usually confounded in only these two behavioral outcome measures. And this is a problem which produces that complex tasks deliver simple, non-specific outcome variables. And the relationships to variables of interest, like general intelligence or other cognitive ability variables, can have validity problems and are non-specific in mapping this relationship. So we wanted to try to validate models of mathematical models with correlates of neurophysiological data, like electrophysiological markers in the EEG. And this would enable us to mutually validate the parameters of the mathematical models as well as the electrophysiological markers. We can test formal hypotheses, and we could overcome measurement problems of inter-individual differences, which is a huge problem in inter-individual difference research. And this is the greater framework of my talk here, which I wanted to present you, that you have a little bit idea of what this all is about. So I have investigated the memory measurement model from Klaus Oberauer and Stefan Lewandowski, and we simulated this model to benchmark it for empirical research because it's relatively new and there's no empirical data to it. So first of all, I want to present you the measurement model framework, and yeah, here we go. The memory measurement model framework formally describes which memory processes might contribute to performance in different commonly used working memory paradigms like simple or complex span tasks. It assumes a competitive selection mechanism of memory items at memory recall, and furthermore, a continuously varying memory activation at memory recall. Until now, there is no model framework which implements a continuous strength assumption at memory recall, and the M3 framework claim to fill that gap, as there are multinomial processing tree models, which are discrete state models for memory recall, and there are continuously activation models, but for a memory recognition, like for signal detection models. So this is relatively new, and it is it was firstly implemented in a hierarchical Bayesian framework, and this does allow not only the estimation of subject level parameters, but also the investigation of group differences or experimental effects, as group parameters are priors for subject parameters. And it has several benefits. It's relatively easy to use, it's parsimonious, and it's applicable for a wide range of working memory paradigms, as it is very flexible in his parameterization. So all in all, it's very interesting for the inter-individual difference research we do in our lab. So this was a logical decision to benchmark this new model. And the basic assumptions of the model are that that memory retrieval is a competitive selection from a set of response candidates which belong to different response candidates in a complex span or a simple span task. And this selection of a certain candidate of a response set is driven by the activation of memory items within a memory set, which represents the strength of evidence for the corresponding candidate. And the activation is determined by 3 parameters. The general activation parameter, I do this quick because I did not manage to stop this. The general activation parameter reflects the strength of memory for an individual item. The source of activation refers to all memory items which have been presented during a trial and a typical experiment, but exclude all information about the relation between those items or context of presentation, e.g. the serial position in relation to other items. This information is captured by the parameter C of the model, which reflects the strength of relational memory, e.g. the strength of bindings between a memory item and its serial position. And this is also the greater theoretical framework this model is implemented in. This is the binding theory by Klaus Oberauer. And at least the filter parameter, F, it maps the ability to prevent the encoding of distractors which have to be processed after each memory item in a complex span task. So after that, I will briefly explain a complex span task so that everybody can imagine what it is in case you don't know. And the parameter B represents the baseline activation for all of the response candidates. and is used as a scaling parameter and is fixed to a value of 1.0. And now we have the underlying task assumptions of a complex span task. And I will briefly introduce the different response categories assumed in the complex span model to explain the model equation subsequently. So here we see a typical complex span experiment with an n alternative forced choice recall query. The response categories are represented by different colors, and the illustration refers to retrieval of the first serial position after the encoding phase. So that's why F is the correct item for the first position. This is the item in position. The immediately following distractor for this position, V, is a distractor in position. The other memory items which have to be remembered are classified as items in other position for the position 1, and the distractors at their corresponding positions as distractor in other positions. So if the second possession now has to be recalled, then the corresponding categories will change for each item, as you can see here. See, this is the first item and this is the second one. Now L is the correct item, F is an item in other position. The distractor of F, V, is now a distractor in other positions, whereas M is now the distractor in position for position 2. So this goes on and on and on. So now the model needs the multinomial choice data from a participant running this experiment. And for all the different response candidates at each serial position. And from this, the different parameters are estimated. Those determine the activation of each of the corresponding response categories. And subsequently, the activations are normalized by Luce's choice rule to obtain the corresponding probabilities of choosing a certain category. Yes, you can see this here. I see this. You can see here, this is the activations for the different response categories here. And this is the parameters. It's a linear combination of the parameters. And you see, for the correct item, the activation is the sum of all 3 parameters. And for all other items, it's the sum of only the activation for the general activation parameter, which refers just the general activation for all memory items, not excluding the serial position. And so a distractor in position is basically the same as the activation for the correct item, with the exception that the filter parameter F modulates the activation here. So if you can filter, perfectly filter, then F would be 0, which means that the activation for a distractor in position is equal to a not presented lure, as it's for the B parameter, which is basically an item which has not been shown in the response set. And the distractor, and the distractor in the other position is the same as the item in the other position, like here, which is also modulated by the F parameter. And there are very promising empirical results. The group level parameters of this model show acceptable recovery and can map aging effects in memory decline. And there are no systematic parameter trade-offs, but there are current shortcomings. Like there is no data for the recovery of the subject level parameters. And as we have seen or heard from Hendrik from the diffusion model, this is a very crucial and a very important topic. So, but now it's our question is, which experimental features are important to achieve a good parameter recovery? And this is very important for the application of the model in inter-individual difference research. Therefore, we wanted to investigate 3 main questions in our study. Can subject level parameters be recovered sufficiently precise? Which factors are important of the estimation of subject level parameters, and how many experimental trials are needed for the estimation of subject level parameters? And the main goal was to figure out how to set up experimental designs to fit the M3 parameters. And we did this all using Stan, because we tried it with other sampling software, but the NUT samplers seemed to be the most efficient, and we had very good results, which I will present later. So what was our procedure here? First, we sampled random parameter values, which were then used to simulate data from random data from multinomial data for the model. Then we fitted the model then we fitted the data to the M3 model, and in the last step we correlated the estimated parameters with the parameters we sampled in the first place. As simulation factors, we manipulated different aspects of the response category candidates as well as the experimental trials. So we used a sample size of 100 simulated subjects and the numbers of items in other positions and the structure in other positions from 1 to 5, the numbers of not presented lures, that are the items that are not shown in an actual memory trial, but are shown in the response set for the scaling of the model from 1 to 16. And the retrievals per subject were manipulated, where I had 4 levels from 100 experimental retrievals to 1,000 experimental retrievals, whereas one retrieval is a single retrieval of one position. So 500 retrievals of set size 5 would correspond to 100 experimental, full 100 experimental trials. To account for random simulation noise, we ran every simulation 100 repetitions per factor combination, and this resulted in 10,000 simulation runs in total. As random factors, we implemented a correlation matrix of the parameters, which was sampled between -0.50 and +0.50 from an LKJ distribution with eta equals 5. And for every simulation run, the hyperparameter means and variances were drawn from a uniform distribution in a predefined range, which I will show you then now. So the multivariate implementation in Stan was with the following priors. We used basically the priors of Oberauer and Lewandowski. The correlation matrices and variances were also sampled from an LKJ distribution with a gamma distribution and sigma with the corresponding covariance matrix sigma. And this is the multivariate sampling statement we used. And as you can see here, this is for every model class here, for the simple span and a complex span model. We used uniform distributions to sample randomly for every simulation run a parameter value, the parameter value, the mean of C, and the variance was calculated in the range between 0.125 and 0.5 multiplied by the according parameter value. And we did this for all parameters except for B, because B was fixed as scaling parameter, and for the complex span model, which features F, we set F to 0.2 and 0.8 because it undergoes a logistic transformation during the sampling process. As we can see here now, I will present a quick parameter recoveries from the Stan models I used for this. And these are the recoveries over all observations. And for 100 retrievals, which correspond, yeah, we can't say the set size here because we manipulated orthogonally. So for 100 retrievals, we saw correlations between 0.87 and 0.93. And for 1,000 retrievals, which is a huge amount, we see 0.90 and 0.97 within all observations for the context activation parameter C. And you see here the amount of not presented lures is manipulated in this panel. And here the distractors in other positions are in this panel. And you see it's basically equal over all these factors. We see this very similar pattern for the general activation parameter A. Here for the not presented lures and for the distract in other positions, there is no huge difference here, and the correlations are almost the same, a little bit higher maybe as for the C parameter. What is really interesting is the F parameter, which is basically recovered perfectly. So we have correlations of 0.99 and 1, or 0.95 and 0.98. Yeah, but this parameter has more degrees of freedom, so it should be logical that this parameter will be recovered more perfectly. And this is now really interesting because this is a simulation run with single correlations in a single simulation run, or over all single simulation runs, not the correlations over all simulation runs. And here we see that the amount of not presented lures as scaling data is very important for the model to for the model recovery here, for the parameter recovery here, as there's a linear trend towards a better recovery with increasing not presented lures. This is for the CA parameter as well as for the A parameter on the individual level, and from 0.72 to 0.88 and from 0.86 to 68 to 0.86, which is still a very nice trend and a good for acceptable trend for using it as an inter-individual difference measure. For the F parameter, this shows similar high correlations as for the overall correlations between, I think, 0.9 and 0.95 to 98, with also drops, but overall it's almost in this panel here. We can also see that the mean trends of the residual distributions, which were calculated as the difference between the estimated and the real or sampled parameter values, decrease with increasing retrievals, which should not be surprising, and this approximate zeros. And you see here the number of distractors in other positions, and you see that there's no difference, and the number of not presented lures. And we see for every panel here, it approximates 0 for increasing not presented lures. This is the main message of this slide, as well as here for the general activation parameter. And for the F parameter, the means were nearly zero for all conditions, which is also not that surprising. So which key features are necessary for an experimental task? We have these 3 main research questions. Can subject level parameters be recovered sufficiently precise? Yes, with acceptable to very good fit. Which factors are important for the estimation of subject level parameters? A sufficient number of NPLs are very important. The more the better. A minimum of 8 should be used to scale the response set of the the number of distractors are less relevant. And how many experimental trials are sufficient for the estimation of subject level parameters? 250 retrievals minimum. I provided you a full working example of one simulation run in my Markdown notebook, which you can just run and see a recovery for a single simulation run, a recovery, and all the needed functions to simulate multinomial data, as well as the 2 Stan models and the Stan codes for applying the model, which can also be found on my GitHub account. Yes, so thank you for having me, and I hope you have some nice questions for me.
Okay, thank you very much, Jan. So again, you can post your questions in the chat. And in the meanwhile, I have some stuff to ask you. So one of the things that something that wasn't entirely clear is what exactly are you fitting? Is it accuracy, or is it like the whole set of responses that the subject gives?
Yeah, we fit the whole. We fit the multinomial choice frequencies of the different response categories. So how many times a participant selected the correct item, the item in position, or how many times the participants selected a not presented lure or a distractor in position. So it's not applicable to reaction times yet, but to multinomial data. Yeah.
So it's essentially it's like a multinomial processing tree, like a configuration of M.
Yes. And it can be also like Gidon Fishcon showed 2 years ago or a year ago. You can I can't find a word now. You can take it as I
Equivalent?
Yeah, it's equivalent. You can mathematically show that it's the same. The parameters of the multi-mean MPT model and the M3 model are, I think, correlated to 1 if you just rewrite the formula. Yes, maybe that's
Okay, but I guess that since you have an activation, you have the potentially you could fit reaction times if you have some linking.
Yes, it really depends on the choice rule you use. I think Obauer and Lewandowski used the Luce's choice rule in the first place because of some mathematical advantages. The next step would be now to maybe include a choice rule which can also handle with reaction times as a natural step to develop the model more. Yeah.
Okay. Okay, in the meanwhile, if there are no more questions, so I have another question. So, and are you considering some other competing models that you can see if there is mimicry, if you can really distinguish between this model and other alternatives?
What do you mean with
other
competing
models that can
models?
explain the same phenomenon? I don't know. To my mind, it pops up ACTAR, for example.
Again, the last I can't hear.
Yes, do you know this architecture?
I acoustically did not get it.
ACTR. ACTR.
ACTR.
Yes, it's just an architecture that potentially could explain also something similar. I was asking if you are considering alternative models that can explain the same data.
In the first stage of our research project now, we just try to fit it with and show that the individual difference parameter can be fitted with acceptable precision. The next step, of course, would be to then try competing models for the data we now produce with empirical data we produce now. It's already we're already planning a study to fit empirical data with the model, and it's naturally that we then will also think about competing models which maybe could be used to fit the data as well. Yes, that's
okay. So there are already a couple of questions. So Gang is asking, is the number of retrievals the same notion of trials in other experiments, psychometrics, fMRI? It's very interesting that you need 500, 1,000 retrievals because that's a close similar ballpark in my simulations under totally different scenarios.
Yeah, I think it really depends. The 1,000 retrieval, the amount of 1,000 retrieval was more or less over the top. I think 250 to 500 retrievals would be a realistic number of retrievals in a behavioral experiment and to fit the data. For us, we want to bring it to the EEG, so we will probably need a lot more trials to calculate the ERPs or the spontaneous EEG or the activation, the contralateral alpha activation, or so on. So yeah, I think it's quite in that range. Yes.
Okay, and Johannes Algermissen is asking how much do such models benefit from hierarchical modeling? If you do single subject fitting, will the model tend to yield large unrealistic outliers? Bottom line, how important is shrinkage, partial pooling for this kind of models?
I really don't know because we didn't try to fit it for the single. We just did not try it to fit it for a single subject or without hierarchical model. Yeah.
Okay, then if there are no more questions, I'm going to share my screen again as a reminder here. So basically, these are all the presentations for today. You are welcome to join to GatherTown, and then we can ask more questions if you now remember something that you wanted to ask to the previous presenters, or maybe there are other people that are interesting to talk with. So yeah, so if you face any problem, just contact me, but otherwise we can all meet for a while, at least it will be open for at least an hour and 15 minutes.
Could you maybe post the link of the GatherTown in the chat once more?
Yes, it's
Thanks a lot.
I hope it works, that this link works. It's also in the landing page when you accept the conference. So there is a Zoom link and below another type of link. I don't know which one is the right one. I think that both of them lead you to the same place. But if you face a problem, this is the time. You can tell me, I will leave the chat open. Okay, thank you, Luco. Thank you, presenters. It was super interesting, and I hope you will join me for a while at least in